A brief forward to this portion of the tutorial. There was a node I neglected to add in during the recording of this that lets the material work properly outside of the instant preview window. For the tutorial portion, I used this window to showcase all of the parts that we were making. This worked specifically because the object center was located at 0, 0, 0 in the preview window here, meaning that any values local were also treated the same as any world positions. This means that if anyone watching this tutorial was attempting to actually use the world view as they were trying to follow along, they potentially will get nothing showing up on screen or very, very wonky results basically if they have any values here. You can kind of see how it's doing something very different. To fix this, what you need to do here is add in a transform node. A transform position node specifically, which translates a local space coordinate to an absolute space, world space coordinate. All that's required then is taking this node here from out of the append and basically plugging everything through there. This won't affect at all what you're seeing inside of the instance material. This will still treat everything properly. So all of our changes here will work fine. But it will mean that everything now in the world position that we see out in the actual outliner scene window will actually work properly as well now. For this last portion here, we're back in Unreal Engine, and we're going to begin by importing our mesh that we've just created into Unreal Engine. I've created here a tutorial map. It's just a quick default level here that we can use. And I will go ahead and import Crag. And there are a couple settings you want to make sure that you have set correctly here. The first being combine meshes. If this is unchecked, what will happen is your FBX will take every fragment that it sees in the file and spit it out into a separate static mesh file here. This is useful if you're using an FBX to kind of store like a large number of different props, etc. For example, if you simply have a collection of chairs or doors or other things, and when you bring it in, you want to bring in one file and have it just divvy it up into all different separate static meshes, it's fantastic. It's great for that. But for our case, we actually want to leave it as a combined mesh. Additionally, we want to make sure that we're importing our normals. Second to last, we want to make sure that we're not converting the scene. If we convert the scene, it will realign Crag and he will be sitting down again. We specifically want to leave him with that Z-up orientation. And we don't need to create any material here. We're going to be creating our own and applying it to him. Now that Crag's actually arrived here, I'm going to go ahead and drag him into the world. Just kind of realign so that I can see him. I'll probably go ahead and delete this ground plane just because it's going to be in our way. And then we'll create a material. We're going to call this our tutorial pivot material. And I'm going to create at the same time an instance of this, simply so that some of the parameters we'll be creating here we'll be able to adjust and see in live real time rather than having to wait for it to recompile over and over again. I'm just going to open both of these up for later. And then we're going to talk about what we see here initially. This first node that you see here, you'll probably be very familiar with. There's a lot of good tutorials out there on how to make materials and such using base color, metallic, specular roughness, etc. For our purposes, though, we kind of want to access some of the deeper levels of a shader. I mentioned the fragment shader and the vertex shader. Just for reference purposes, the emissive color node is how you get to the fragment shader. But for us, we want to access the vertex shader, and we're going to do that using the world position offset pin. The world position offset pin specifically adds to the vertex position. It does not replace it. So if I go ahead and hold down V just so I can add in a node here, that's a color, I can go ahead and plug this in and compile this. And in case you haven't known this about Unreal, you can actually click on a static mesh here, and if you jump into a material, you can set it as a preview using the teapot. And I'm going to do the same thing in this window here. And now what I can do here in our instance of this, I can turn on this parameter, and if I, for example, adjust the blue channel, which for us is the z-axis, you can see that I am adding as I change or subtracting from the vertex position in the z-axis. So any changes or any additions here will be in addition to wherever that vertex is known to be located in world space normally. The next thing to talk about is going to be how can we get information about our vertices and our pivot points. There are two good nodes to know right off the bat. First is going to be our object position. This is going to give us the object center in world space. The other node is going to be called world position, and this absolute world position is going to give us our vertices location in world space. The next node is going to be a texture coordinate node. And this is a node that if you've done materials beforehand, this is how you grab your UV data. But you may not have noticed that you can actually indicate which UV map you want to use. It's by default set to 0, and we have stored information to both UV1 and UV2. So I'm going to create 2 of these, and we're going to use the UV for the first one for our XY. And I'm going to append to it using the append vector node. And then a mask node, because I specifically from the second one only want the R channel, which is going to be that 0 index from that third UV map that we made. And now I have our pivot data here. I can actually apply it to our base color, and if we look at Crag, we can see that we do in fact now have his pivot data for each of the fragments that he has. The first most basic thing that we can then talk about using this data is going to be a simple scaling operation. So for a simple scaling operation, just as an example, I'm going to take our absolute world position and I'm going to subtract from it our object center. And I'm going to give myself a scaling parameter here so we can see. And I'm going to multiply this vector that we've created, because in vector math, a position minus another position creates a vector from the first, that's from the second pointing towards the first. So this vector for us will take a point, for example, like his arm up here. Here's his center. So we're going to do his arm position minus the center, and so we'll get a vector pointed outward. And if I multiply this then by our scaling parameter here, and I attach this to world position offset, what we'll get here is we will get a value then that we can adjust that will actually scale and shrink him as we are used to seeing in any other program. If we end up, instead of using his absolute world position for each of the vertices, if we used the baked vertex position that we created instead, and I apply this, what will happen is we will take every vertex that is part of a pivot or a part of a fragment, and we will give it the same direction and the same magnitude of movement, meaning that we will actually get to see him and all of his pieces as they expand outward as a group. And so this is the concept then. We have a series of vertices that have an importance associated to each other based upon their pivot point. And so we can now begin performing other operations, rotation, translation, etc., using this pivot point instead of their absolute vertex position, and we will treat the fragment itself as a single unit. The next thing we want to talk about then is rotation. So what we're going to do is we're going to add in a node that will let us rotate each of the fragments around their own pivot point. I'm going to right click and type in rotate, and I want rotate about axis. This node requires a normalized rotation axis, a rotation angle, a pivot point, and a position. The position's the easy one. The position we actually want to rotate, we want to move around, is going to be our absolute world position, so wherever the vertex is located. Our pivot point, we said that we want to rotate it around our pivot point. And our rotation angle is going to be some other scalar value that we're going to simply assign. So this is going to be rotation. Plug that in. And then normalized rotation axis. This wants to know what axis we want to rotate around. And so for this example, I'm just going to hold down V, and I'm going to leave this here as 0, 0, 1, meaning that our axis of rotation is simply a vector pointing straight up in the z-axis. I will plug that into our rotation there. Now I'll go ahead and plug that into our world position offset instead. Hit apply, and we can take a look now at our pivot instance. And now, as I rotate this object around, you can see that all of the separate pieces are rotating around their own pivot point. What if I want to combine these two motions, however? If we want to combine these two motions, it's actually not too bad. In order to add these two transformations together, all we actually need to do is add them, literally. So now I can scale this object in and out and rotate all the points around their own local origin. And you'll find that most simple transformations are like this. Because these transformations are linear, they can be treated simply as A plus B plus C, mostly. The place that you're going to find some confusion in is anytime we deal with rotation, and you need to be somewhat careful. So I recommend when you're building more complex animations and such with this, build them up slowly and have a very clear concept of what it is you want to accomplish. So for our last part here then, let's start making a little bit more complex of one, just so we can kind of talk about and push that more complex behavior. So right now we have the object where we can scale it inward and outward. We can rotate the pieces around themselves. Let's also allow us to rotate the object, the separate fragments themselves around the center of our object, and let's give ourselves the ability to scale them individually on their own. So in order to add in the next portion, which is the rotation around the center of each of the fragment pieces, we're going to need another rotate about axis node. We know that we want to use the center as our pivot point, but what do we use for our position? Well, the issue here comes down to we can't specifically just use the vertex position as it currently is. This is because the position has been changed once we have it run through our scaling portion, where we start moving these different fragments outward. So we actually need to use the movement of the fragment itself and add to that its initial position. And we can then use this as the position that we are going to rotate. I can go ahead and copy this just for clarity's sake and use this as well for our axis of rotation. And then for the rotation amount, we just need a different scalar value. And so I'll plug that into our rotation angle. And to see this in action, I need to then add this into our system here to show the output. What I'm going to do here, though, is I'm going to remove our rotation about our center axis, and I'm simply going to add this to our scaling and then use that in our world position offset. And the reason for this is we need to make sure that we add these together because we're first moving it out and then we're rotating around. If we come over here to our instance, we can then see I can still scale and shrink it properly for each fragment, and I can rotate then the points around the center of our object. We can then go ahead and add in this last one. And then we can go back and double check that everything is working properly in the instance. Our rotation still works. Sorry, our local rotation still works. Our rotation on the center still works, and we can still scale properly. The last thing then to add in is the ability to scale each of these pieces individually. So to scale all the pieces individually then, what we need to do is simply take our absolute vertex position and then subtract it from the vertex position. So now we have a small vector based around each of the individual pivots. We'll give ourselves a new scaling value here. This is local scale. Multiply that out by the vector we've just created. And go ahead and add that in. And when we add this in, we're going to see a quick little small issue here. And I want to illustrate this as the importance of, as your network potentially becomes more complicated, you're going to have to make sure that you understand the order in which you want to perform these operations. So now if I scale these down, you can see that we're scaling them down in the, looks like just the z-axis and such right now. If I reset all my other values back to 0, we can see that this is actually acting as we potentially expect it to. So which of the things is it actually having an issue with? And the thing it's having the issue with is actually the rotation itself. And the reason for that is the local rotation. Then you'll remember that each of these objects here, as they're rotating around their center, they assume they're in one position rather than in another. And so what we need to do is actually bring this value here of our shifted vertex offset for our local scaling back to this rotation axis that we're doing for our local rotation. But remember that just like we did for our rotation around the center, this is an offset change. So we do need to take our current position and add our offset to it, and then we can use that. And we're going to get a little bit spaghetti here because of that. But once we actually add that and apply it, we can now grow and shrink our points. And so -1 actually will basically be gone. They'll all be scaled down to a point. We can still have them rotate around as they're expected to, and then rotate around the center and scale them in and out. The last thing that we need to fix then is the normals of our object. The reason for this is just because we're rotating our object, or rotating the points around our object here, the program is not assuming that anything has changed with our normals. So you can see here that our lighting looks very strange, and in fact if I begin rotating these objects, if I go back to 0 here, the light isn't really changing. You can see that as I rotate this, the light on the pieces is not changing really. And so we need to actually add one more node in here, and there is a fix rotate about axis normals that we actually need to use to fix our normals. And all we need to do here for this node, we don't actually utilize all these pins. Our rotation axis is the -1 axis. It's the same one as this. Well, actually, we'll use this and we'll bring this up here. And then our rotation angle is this node. And now we just need to plug in our new tangent space vertex normals. And now all of our normals should be correctly calculating, and you can see that they're looking much better when they rotate. They're occasionally catching the light now, and they're actually treating the light as it's supposed to be. So now you can kind of, if you want, you can take this kind of thing. You can use, you can use a time node, and you could begin driving things with it, a sine wave, other kinds of interesting stuff. Plug it into material parameters or the mesh component parameters. There's a lot of stuff you can end up doing with this to make it more interesting and procedural. But this has hopefully been an interesting and useful introduction into what UV pivot baking is and how to actually go about doing it. Thanks for watching.